Yeah, I think at some point it says if you want to attend graduation, it's like maybe they'll send you an email. Okay, congratulations. Oh yeah, you know, you didn't have to go. Yeah, so we just had funny sleep and I was like, excuse me. Yeah, like, graduate, yeah.
Okay, so let's talk about NP-completeness. NP-completeness is a theory of complexity, of computational complexity, of tractability. What's possible or not possible to do efficiently, what kind of space or time consumption or any other resource for that matter, not just space and time. So typically we identify tractability, efficiency, with things that can be done in polynomial time. So we watch the clock while we compute, obviously. Time matters. It could also be space. And often it's easier to verify than to compute. So for example, to find if a sequence of numbers is already sorted, you can do it in linear time. But to actually do the sorting yourself, that's n log n at least. So there's sometimes a separation between verification of an answer and the actual computation. You may have noticed that, when you solve problems, if somebody gives you the solution, it's much easier for you to verify that they're right than come up with the solution yourself. That's another example of computation versus verification of an answer that we already have. One is not like the other. And it's also the power of non-determinism. Non-determinism is a branching of the computation, not just a linear, serial, deterministic computation, where every state has a unique next state. For non-determinism, each state can have several next states, and it's a model of parallelism. So that's a very critical kind of aspect of NP-completeness. You want to know what non-determinism buys you in terms of efficiency. And it's about encodings of problems as other problems, transformations of problems to one another. We already saw a bunch of examples of encodings and transformations of problems to other problems. Right? We reduced sorting to convex Hall. If you can do convex Hall efficiently, you can sort efficiently by reducing an arbitrary instance of sorting to a particular instance of convex Hall. How many remember that? It's a lower bound proof. You'll see a lot more of these coming up. We've already seen a bunch before. And it's the comparison of polynomial time solvable problems to non-deterministic polynomial time solvable problems. So the former is called P and the latter NP. So you've probably seen this P and NP kind of stuff before, and we'll go pretty deep into it. And it's a theory of completeness. If something is NP-complete, it's as hard as anything else in NP. So this theory of NP-completeness allows us to find the hardest problems in a particular class. And not just P and NP, there's this kind of theory for lots and lots of other classes of computation. Right? Long space and linear time, and exponential space and exponential time, and even much higher categories. So the theory is very general. Why do we study it? Let me count the ways. It saves you time and effort. If you could show a problem as NP-complete or intractable, many other problems become intractable too because they depend on that problem for their solution in some intrinsic inherent way. So if you can show that the problem reduces to another problem And that other problem that it reduces to requires, a lot of space or time. You can infer some stuff about the unknown problem. So it allows you to infer the difficulty of lots of problems in a particular class, not just one or two or one at a time the hard way, but makes you able to infer things about large classes of problems simultaneously. Together they stand, together they fall with respect to intractability or efficiency, whichever may be the case. And also it saves you trouble for trying to solve hard problems, intractable problems efficiently. If you know they're NP-complete or NP-hard, there's no point in trying to come up with a fast or linear time algorithm for them, because either there's none or it's at least very, very hard to find one. Because if you found one, an algorithm for an NP-complete problem, all of P would be equal to all of NP, and then you'd be solving $1 million problem. Literally, there's a bounty of $1 million by the Clay Institute of Mathematics to show or disprove whether P is equal to NP or not. So it saves you, it's a negative result, and it's also a positive result when you know something is NP-complete. Also, it can save you money. If you're a company, don't spend money and resources and energy solving or trying to solve NP-complete problems in an exact algorithm, precise solutions. Try to use heuristics instead. And historically, many people, many companies, thousands of them, have made these kind of mistakes by not paying attention to the theory of NP-completeness, which would have saved the day if you only knew about NP-completeness theory more. You can leverage the work of others, because these problems are reducible to one another. So when somebody comes with an effective heuristic for one, that immediately translates into effective heuristics for many other things. Right? We already saw, for example, that convex hull can be used by sorting efficiently and then doing some scanning in linear time. Well, so if you have a better algorithm for sorting, you immediately have a better algorithm for convex hull, because that uses sorting as a subroutine, and that's the bottleneck in the convex hull algorithm, is the call to the subroutine algorithm. So in NP-completeness, we see a lot of that. You can leverage the work of others by incorporating their efficient algorithms to come up with efficient algorithms of your own. And conversely, if you can show that the two are tied together, one can be reduced to the other for a limited time, and one of them you can show is intractable, not solvable, efficiently, then the other falls into the same category automatically. So a lot of lower bound kind of arguments come out from that. And transformations can be used to solve new problems by reducing them to known old problems. Right? So if you're not sure how to, use convex hull to compute something else, and without the convex hull subroutine, that something else may have been not easily computable efficiently. That gives you a lot of leverage. So, and also it illuminates the structure of and the relationship among seemingly unrelated problems. Before, we didn't realize that, say, Boolean satisfiability is inherently tied to, say, traveling salesman problem. One is about graphs, one is about Boolean formula. How can they be related so intimately? Well, they're both NP-complete, and all the NP-complete problems are related to each other in these interesting ways. So when something's NP-complete or NP-hard, you should use approximation algorithm, not exact, solution. You should use heuristics or approximations, not look for exact answers like traveling salesman and bin packing and graph coloring and that kind of. So we can avoid wasting needless time and energy and possibly a lot of money of R&D trying to find exact solutions. Algorithm needs exact solutions. So it gives you a license to use heuristics without the embarrassment of one day somebody coming up with an exact algorithm that runs very quickly, and you were running heuristics because you didn't know any better. So it tells you exactly when you should and you shouldn't. You should not use heuristics versus exact algorithms that give you precise problem solutions. Also, it helps understand the underlying structure of parallelism. Parallelism is a very tricky business. Edgar Dijkstra studied parallelism at length and came up with, mechanisms like semaphores and how you use parallel programming kind of techniques over time, a bunch of you. So parallelism is tricky business, and the theory of NP-completeness sheds light on how much parallelism helps or doesn't help in various scenarios. And that's always good to know. Some problems, even if you parallelize a solution, it's not going to do you any good. You want to know about that if that's the case. So it enabled very general studies of completeness theories, relationships between large classes of problems, helps explain why verifying proofs seems to be easier than actually coming up with these proofs in the first place, constructing these proofs. Like we said earlier, verifying or checking somebody else's solution is easier than coming up with your own. And it illuminates the fundamental nature of algorithms and computation in a very deep and meaningful way. I mean, I know these are a lot of selling points, and now you're probably eager to see the actual stuff that has all these wonderful properties, but you will. It's pretty amazing, actually. It slices, it dices, it's like the insulin. That's a lot for you. He gave rise to whole new ways of proving things. In studying completeness, people come out not just with new theorems, but with new ways of proving theorems, meta proof techniques, and that's always valuable to have more proof techniques and understand how they work and where they can be applied. And you can always benefit by manipulating and understanding and solving large classes of problems simultaneously rather than individual ones one at a time. And because this allows you to pull this off. And it decouples abstract complexity from the actual models that are implemented in the real world. So NP-completeness talks about the inherent complexity of problems, not the complexity of solving them on a Dell computer versus an Apple computer versus an iPhone versus an abacus versus some super duper hyper quantum computer. No, it actually talks about the problems themselves and addresses their intrinsic complexity. That's always good. That's more fundamental. Sorting has its own intrinsic complexity of n log n lower bound. Whether you run it on a Mac or a PC or a Dell or a Linux machine or a supercomputer, or even run it on an abacus very slowly, sorting is still n log n in all those cases. It's a property of the problem, not a property of the platform that's used to implement and run that problem in any particular instance. So NP-completeness kind of abstracts or decouples the complexity of problems from the underlying technology. So it's applying to every technology. So there's an alien, race somewhere out there in the universe that does computation, has compute, NP-completeness will be applicable to them and their technology, even though we have no idea what they are and what their technology looks like. But that's how abstract, robust, general that theory is. It gives you a handle on how to identify and prove certain problems are the hardest for their class. You have a large class of problems. These classes are infinite, by the way. They're not just 13 problems put together. There's only an infinite number of problems each one of these classes we're talking about. Tells you how to identify the hardest problems in the class. Which is an interesting feat to be able to accomplish. And it forged whole new unifications between math and computer science, and even logic, and even philosophy. So it did all that. But let's never underestimate, a really good reason to study anything. It's fun, it's interesting, it's intriguing, it's pretty cool. Okay, so with all that, let's start diving into it. So you can say a language, really, when you see the word language, you can think about it as a problem. Problem A is reducible to a problem B if there exists some function that takes you from the first to the second, first set of instances of the first problem to an instance of the second problem, where that function preserves membership. If the first instance of the problem is an element, or is a true instance, a yes instance of the first problem, then the second is an instance of the second. The transformed version of the problem instance is a member of the second problem. And by problem, usually we mean in NP-completeness, usually it's yes/no questions. We'll show you later why asking yes/no questions is as general as asking arbitrary questions. Okay, we'll get to that in due time. So that's typically what a reduction is. And it's called a reduction of A to B. A is one set of instances, like if it's a sorting problem, then you have a bunch of sequences in that set A. Each sequence is a sorted sequence. So when you sequence comes by, the question is it sorted or not? If it is, it's a member of A. If it's not sorted, it's unsorted for any reason, it's not an element of A. So A is a problem, and its instances are yes instances. So it's something sorted or not. Is something a perfect square or not? Is something a prime or not? Okay. And turns out you can couch any problem you want as a yes/no instance. I give you a graph, and I say, here's a tour of the graph. Is this the best optimal tour? Yes or no? And if it is, it's a traveling salesman tour. If it's not, it's something else. But that's what we mean by yes/no questions or problems. Okay. And we denote it as A reduces to B, and this overloaded symbol here is, it's not the less than or equal to that we know and love from arithmetic. It means it's a reduction in this sense. Okay. Let's put this in the context of sorting and convex halls. So you can say convex hall, let's call it problem B, and sorting is problem A. And so, sorting reduces to convex hall. Why? Because you take an instance of sorting, a permutation that's needs to be sorted, and then you transform it into a convex hall instance such that if you had a convex hall instance, you knew how to sort the original permutation. Examples like that we know and love and have already seen a number of times kind of fall into this large kind of abstract notation, if you will, or schema. And intuitively, it means that A is no harder than B, because if you can reduce A to B, once you solve B, A is automatically solved. If you can solve convex halls, you automatically can sort from that reduction that we saw many weeks ago. So that means convex hall is at least as hard as sorting. Or conversely, it means sorting is no harder than convex halls. You can look at it from either direction. So, having said all that, now we impose a time clock. You say this problem or language is polynomial time reducible to this other one when this f can be computed in polynomial time. The transformation itself needs to be done efficiently. Again, back to the example of sorting, reducing to convex hall. If that reduction of sorting to convex hall by squaring all the points to be sorted, raises it into a parabola, and making it a convex hall instance in 2D, if that process took more than linear time, if that process took quadratic time already, the reduction wouldn't show you a lower bound for convex halls. How many sort of can see that? The process of transforming one to the other itself has to be done efficiently. Otherwise, any kind of lower bound inference that pops up at the end may be due to the transformation itself, not to the actual problem. Okay. So, if you're wrapping gifts, you're buying gifts at a store and they wrap it for you, for free or whatever, the cost of the wrapping better be no larger than the cost of the actual thing that gets wrapped, the gift itself, at least ideally. Otherwise, it's kind of inverted in the economics sort of that. So we watch the clock while we do these transformations, while we compute, and that's where original sort of non-timed or non-resource bounded reducibilities or reductions become bounded, resource bounded reductions. In particular, polynomially time bounded. Because you can bound that time by other things in polynomial. And you don't even have to bound the time, you can bound the space or many other resources that you consume as you compute. Right? So now we're saying f is a polynomial time reduction from one to another. And you put a little p there to show it's polynomial time. And that's kind of the basic definition of reductions. And again, remember, we've seen a bunch of reductions already. Question?
In this context, does f also include the transformation from the answer of b to the answer of a that you wanted originally?
Yeah, but it transforms the instance, not the answer. Remember, these are yes/no questions.
Okay.
So if it's yes there, yes, it's a yes there. If it's a no there, it's a no. So yeses go to yeses and no's go to no's. So in some sense, the answers get transformed, but it's kind of a trivial matter because a yes is a yes and a no is a no. We'll say a little bit more about that later on. Well, okay, let's say something about that right now. Why is yes/no questions as general, almost as general as arbitrary questions? Let's say I'm thinking about an animal, some species of an animal, some specific animal, and you're trying to find out what animal I'm thinking about. And you can ask me, say the name of the animal. But what if I can only say yes/no to questions that you ask me about that animal? How would you figure it out? A lot of questions. How many questions? Millions? Let's say there's a million different species of animals. How many questions will it take you? A million? Log of a million. Yeah. It'll take you roughly a logarithmic number of questions in the size of the space. A log of a million is about what? Powers of 2. Magnitude. What's a log of a million? Base 2. 20. So just to be on the safe side, how many questions should you ask if you're clever enough? 21. Now you know why that game is called 21 questions. How many write that game 21 questions? Yeah, so how would you figure it out? And there are about a million species that people know, well, actually less than that people know, and more than that technically from a biological sense. First you'd ask what? I'm thinking of an animal, we try to figure it out. Let's play around with this. It's just for fun. Ask me questions. I'm thinking about an animal, you need to figure out exactly what I'm thinking. Ask it.
Is it a mammal?
Yes, it's a mammal.
Is it extinct?
No, it's not extinct. What else? So that's 2 questions.
4 legs.
4 legs? Yes.
What geographical location will you find it in a world?
That's not a yes or no question, so I can't answer that.
Can you find it in Africa?
Yes.
Does it have fur? Does it have fur?
Fur? I'll say yes. But doesn't mean it's got fur all over its body necessarily.
Is it an elephant?
No,
If
it's not in Charlottesville. That I know of.
Is it a giraffe?
Not a giraffe, no. Donkey? No.
Is it cool? Does it eat meat or?
No.
Could you write it if you wanted to?
Yes, that's 11. Yes, does he eat meat? I don't think so. I'm not an expert in biology, but I would say no. So that's 11 questions.
Does it have horns?
Horns? Does it have horns? No. That's 12. Is it a carnivore? No. You already asked it, so we won't penalize that question.
Is it bigger than you?
It's about 12, 13 questions.
Is it bigger than you or smaller than you? Like an adult average.
Ask me a yes or no question.
Yes or no?
Is it bigger than you? Yes.
Is it gray?
You can write it, but somebody already asked that, so that's still 13. Is it an elephant? No. That's 14 questions.
Does it have stripes?
Yes, it does.
Zebra.
Ask me yes or no question.
Is it a zebra?
Yes, it is, and now we're done.
Is it zebra?
Okay, yeah, it's a zebra. So notice, if you go back over the questions, I was correct with each answer, and that really helped you narrow it down. Out of millions of species, you finally figured it out, and you took less than long questions. I mean, maybe it was 15 or 16, whatever it was. So, this membership here is yes/no, but that's not restricted, because that encompasses lots and lots of non-yes/no questions and answers by this game of 21 questions. So if you can answer yes/no within a long number of iterations, you can answer arbitrary questions. Right? If nothing else, you could have asked me this: in the spelling of this animal in binary, is the first digit of its name a 1? And I would say yes or no. Is the second digit 2, a 1 or a 0? And eventually you squeeze out of me all the bits, and then you just interpret it as a character string, and then you know it's Z, E, B, and so on. So at the very least, you can always do that. But that's not a very interesting game. It's more fun to ask about fur and legs and carnivore and that kind of thing. But the point is, 21 questions is a very powerful way of converting arbitrary questions into just yes-no questions, and still avoid asking too many of them, and always get the right answer. And NP-completeness has a lot of that going on. So with this intuition, we can proceed, and we'll kind of point that out later on. So a few theorems come up right away from this kind of abstraction, reducing a problem A to problem B. If A reduces to B and B is solvable, decidable means just solvable. And in complexity theory, decidable means has an algorithm. But solvable within polynomial time, then A is solvable within polynomial time too. In other words, if A reduces to B and you can do B efficiently, then you must be able to do A efficiently too. Why? Because even if you don't know how to do A whatsoever, but you know how to reduce it to B, then you can do B efficiently, that's how you solve A. Convert it to B, and then the solution to B will translate immediately the solution to A because it's yes-no. So yeses become yeses and no's becomes no. Membership is preserved. Remember, this is a member of A if and only if its transformation is a member of B. It's an if and only if. So this mapping preserves membership. Yeses become yeses, no's becomes no. Okay. And if A reduces to B and A is not solvable within polynomial time, then B can't be solvable in polynomial time also. Right. So if you reduce A to B and B provably cannot be done efficiently, then neither can A. So, by the way, these two theorems, one is they're both really the same theorem. How many can understand that? Or see that? If A reduces to B and B is efficiently solvable, then so is A. If A reduces to B and A is not efficiently solvable, then neither is B. Because one way to think about the second theorem is that if A reduces to B and A is not efficiently solvable, then B can't be efficiently solvable either, because if B was efficiently solvable, you'd be able to solve A efficiently too. Why? You don't know how to solve A, so transform it to B, then solve B efficiently, which is not true, and then that will be immediately translate the yes to a yes and the no to a no, and you'll be solving A efficiently, which we said you can't do. So, also, the second one is a contrapositive of the first. How many can see that? Okay, good. So you're with me. So we proved it kind of independently, but it's really the contrapositive of the first. So if you say something, if you have a logical statement that says, if A then B, or let's forget A and B because I don't want to overload this two symbols A and B. If you say if P then Q, that means that not Q implies not P. That's what we mean by contrapositive logic. Okay, and you have to be very careful which way you reduce, because these are one-way reductions. So if A reduces to B, doesn't mean this thing reduces B, instances of B to instances of A. So if you know how to reduce sorting to convex hull, doesn't mean you know how to reduce convex hull to sorting, even though you can do that separately with a different reduction on the side, but one doesn't imply immediately the other in an obvious way. Even though reduction can still exist, it's not the same reduction. Okay. We'll see more examples of this. I know it's abstract, but I try to couch it in simple examples like sorting and convex hull, which we've already seen, and the game 21 with zebras that we just went through. But you'll see more and more instances of this phenomena, and you'll get more and more comfortable. So to solve a problem, efficiently transform it to another problem. So let's say the problem of satisfiability, which you have a Boolean formula. Each one of these variables is a Boolean variable. It can only be 0 or 1. These apostrophes mean negation. I could have written a bar over the x, same thing, not x. So x or y and not x or not y. This is a Boolean formula. The problem of satisfiability is I give you a Boolean formula, and you tell me if there's an assignment of the variables that makes it true. Any assignment you know. I'm asking you, does there exist such an assignment. And then you plug in some values of zeros and ones to the x's and the y's and the x naughts and the y naughts and the z naughts. Is there such an assignment, whatever it may be, that makes the whole formula evaluate the truth? It's a very simple question. Because it's a yes-no question. How do you run into this problem before satisfiability? Okay. We'll get pretty deep into it. Because it's archetypical. And also, it's NP-complete. This is the hardest problem in NP. As strange as this may sound. If you didn't care about time and wanted to solve this deterministically, I give you a Boolean formula and ask you, is it satisfiable? Is there some assignment of the variable that makes it true? What's a simple algorithm to do it if time didn't matter?
Find every possible.
Look at every possible different assignment of the variable. Let's say there's n variables. How many different combinations of the assignments to the n variables are there if you want to test all of them against the formula? 2 to the n. 2 to the n is not great efficient time. Okay, it's exponential. So yeah, you can do it very easily that way in 2 to the n. Can you do it in polynomial time? Nobody knows. This is an NP-complete problem. If you can solve this in polynomial time, you'd win not just $1 million from the Clay Institute. You will probably win a Turing Award, and they'll give you an instant PhD and possibly tenure too, even if you didn't award the professor. That's how hard this problem is. We've been trying to solve that since the early 70s. Whether it's NP-complete, people have been trying to solve that for much earlier than that, actually, but they didn't know about NP-completeness. Okay, but here's what you can do. You can transform this problem, and these sort of little gadgets here are just transform. I use those to denote transformation. This is a little Turing machine, this Turing thing, but it's really just a transformation. It's this F on the previous slide. It transforms this problem to another problem, and in this instance, we may want to transform it into a graph colorability problem. And if you can solve the graph colorability instance, that will tell you whether this formula is satisfiable or not. And by the way, what is graph colorability? Well, again, a very simple problem. I give you a graph, just a bunch of nodes and edges connected up in some arbitrary way. And I ask you, is there a way to, say, color this graph in 3 colors or less, such that no 2 adjacent nodes share the same color? Any nodes are neighbors must have different colors. So if you have unbounded number of colors, it's trivial. You assign every node a separate color, a different color than all the other nodes, and that's it. But you don't have an indefinite number of colors, you have 3. And the graph can be pretty large. So some graphs are 3 colorable, some graphs are not 3 colorable. But if you have some engine that solves colorability, a colorability solver, graph colorability solver, you can use it to colorize the graph, say 3 colors, green, red, and blue, and then use that colorability of the graph, this coloring of this particular graph, to solve the satisfiability instance. And in this case, if we set x to 1 and y to 0, this becomes satisfiable. If x is 1, so this clause is true. Y is 0, so this y naught is 1, so this one clause, this adjunctive clause is true, and their conjunction, therefore, is true also, because they were both true, given this assignment of the 2 variables, x and y, true and false, respectively. So that's an example of a transformation. Now, how does transformation work specifically? How do you transform a formula specifically to what kind of graph so that a colorability solver would expose the satisfiability instance, the true yes, the yes, no, true, false satisfiability solution to the original? That's a trip. And we won't see that for a while, maybe until next week. That's a tough transformation to wrap your mind around. We'll go through it. It won't be easy. So it's all about transformations, transforming problems to other problems in a way that preserves their solutions. Yeses become yeses and noes become noes. Okay. Any questions so far? I know this is abstract. We'll get more and more concrete. There'll be more and more examples, and we'll kind of ease into it as we go. Yeah. No, he's asking, does it have to be invertible? And the short answer is no, because what we said earlier, it's not two-way. The transformation works one way. And let me remind you where I said that specifically on the slide. Be very careful about the reduction direction, which way you're transforming. You can transform this way, but you will not be able to transform the other way, using the same or similar transformation. the transformation the other way may be impossible, or it may be possible, but be completely different transformations than in the other direction. Next one? Okay. I will show later. It's a complex proof. I'm just showing it notionally. I'm not saying that this graph corresponds to this formula. The graph corresponding to this formula, given the real transformation of how this actually works for these two problems of satisfiability and graph tolerability, it's a much more complicated transformation that I can fit in this one slide. So I decided to just show it to you kind of generically and abstractly for now. Later we'll see the proof. The proof will be several slides long. And by now you know me well enough to realize that if I say a proof is several slides long, it's really hard because we proved some amazing things on a single slide all throughout the course. So that one you cannot prove on a single slide. But it's a good question. We will answer that when we have enough infrastructure to address it. Right now, it's more notional. Okay, NP hardness and NP completeness. So a problem is NP hard if every problem in NP reduces to it in polynomial time. What is NP? It's the set of all problems that are solvable in non-deterministic polynomial time. P is a set of all problems that are solvable in deterministic polynomial time. And the big $1 million question, literally $1 million penalty on this question, is whether P is equal to NP, whether non-determinism helps with respect to polynomial time kind of differences. And nobody knows that. We've been thinking about it for a good number of decades. Okay, so NP hard is any problem in NP reduces to it in polynomial time. That makes our problem NP hard, because it's as hard as anything in NP. But it's also NP complete if it itself is in NP. So NP complete is NP hard plus one more constraint. That it must itself be in NP. Because for it to be NP hard, we never said that the problem itself, that everything NP reduces to itself, L prime, is also in NP. It could be outside of NP. It could be done, take at least exponential time to solve, or super exponential time to solve, or whatever. So NP complete is more restricted than NP hard. But it also implies that if one NP complete problem is in P, they all are. And all of NP is equal to P. Okay. Why? Because if one problem that's NP complete is in P, remember, it's NP complete meaning everything in NP reduces to it. And if you can solve it in polynomial time, through these reductions, you can solve all the others in polynomial time too. How many can see this logic? Not too many. Okay. So let's revert back to the example of sorting and convex solve. Let's say we had no idea how to sort. I know it sounds far-fetched because sorting is so straightforward. But let's say we had no idea how to sort. But we knew exactly how to compute convex solve. And we showed that sorting reduces the convex solve through this reduction by squaring all the numbers within a parabola and so on. Then let's say we didn't know how to solve convex solve either. But we knew that sorting can be reduced to convex solve in polynomial time, in fact in linear time. You can create this reduction, square all the points, and that's the reduction. This means if convex solve was solvable in polynomial time, then so is sorting. And in particular, if convex solve was solvable in n log n time, then so is sorting. Because this transformation only took linear time. That's, and any problem can be reduced to convex solve in linear time, can also be solved in n log n time, assuming convex solve can be solved in n log n time too. So in one fell swoop, you can solve lots of problems if you show that a large class of problems all reduce to convex solve in linear time. And once you have an algorithm for convex solve that runs in n log n time, they all run in n log n time, automatically. How many get that? Not just sorting. Okay. So that's what we're talking about here in general. Okay. One of them is in, all of them are. In where? In P, solvable in polynomial time. So here's P, the set of all problems that solvable in polynomial time. And here's NP, it includes P, because determinism is a special case of non-determinism. Let me not be presumptuous. How many have heard of or dealt with or analyzed or heard lectures or read stuff about non-determinism? Okay, a lot of them. Good. In computer science theory, and the equivalent here would be, I guess, 3102 in our department. Computer science theory, they talk a lot about non-determinism and non-deterministic Turing machines, and it's a whole area to itself. But for now, in this discussion, let's just say it's stuff that can be done in parallel. When you do stuff non-deterministically, you're only being charged for the depth of the computation, not its width. You're being charged for the depth of the tree when the tree bifurcates in different states in different directions simultaneously. You're only being charged for the depth. That's your running time. Because it's all running in parallel. So if you're running a bunch of things in parallel, you're paying for the slowest process. The other processes will either be quicker or they're just as slow, but not any slower than that. How do we understand that? You're being charged for the slowest thing if you're running a bunch of stuff in parallel, and you have unbounded number of processors, or threads, or whatever you want to think about it, or when you're doing non-determinism. So here's P and here's NP, and P is a subset of NP, we know that for sure, because now you can answer the question, why is determinism a special case of non-determinism? Non-determinism, there could be many next states. There can be many next states, not just one. Determinism is, there's only one next state, it's deterministic. What happens next is exactly, completely a function of what happened previously and nothing else. There's no other options. Non-determinism, there's options. You can move left, right, lots of different ways from any given state. So why is the non-determinism generalizing determinism? Or conversely, why is determinism a special case of non-determinism? It's a very simple question. There's nothing tricky about it. How would you answer that? Why does one subsume the other so that we have this set relationship and one is a subset of the other? Let me back up a second. How many understand what P is? Yes. Then tell me the type of P. What is P's type? Is it an animal, vegetable, or mineral? What is its type? So for example, the type of pi, pi is a real number, so is E. I is an imaginary number, that's its type. What's the type of P? What is it? It's a set. How many see P is a set? Good. Now tell me, what is it a set of? It's a set of minerals, vegetables, or animals, and what are the elements of P? What are their types?
Problems.
Problems. What is the type of a problem in this scenario?
Solved and polynomial.
That's a characteristic of the problem, but that's not its type. A problem you can think of as a language of strings, just a set of strings. With all the yes strings. So you can think about the language of prime numbers as all the prime numbers. Strings made up of digits, each one is a prime. So the string, quote, 3, unquote, will be a member of the prime language of primes, or the problem of primality. So is 5, so is 13, so is 49. They're all prime numbers. Take all these numbers together as strings, put commas in between them, put braces around the whole thing, and get a language or a problem. And so whether a number is prime or not is simply a question of, is that number an element of that set that I just described, the set of primes? So it's a yes-no question. So the type category of a problem is, it's a language is a set of strings. It's a formal language. When I say language, I don't mean English or Chinese or Russian. I mean, a language is just a set of strings. So the language of English is all the words in the English language. Actually, it's all sentences, all grammatically correct sentences in the English language, not just individual words. So just make sure you know the type of these objects. So P is a set of what? A set of sets. Each one of those sets is a sequence or a bunch of collection of strings. or elements representing strings, however you want to think about it. Okay, I just want to make sure you have the types correct in your head. So out here is all problems which are NP-complete, like satisfiability. So satisfiability is a set of all Boolean formulas that are satisfiable, or for which each of which there is some assignment of its variables that makes it true. Because for some formulas, that's not the case. You cannot make it true no matter what you assign a variable. You only get a contradiction or a false when you evaluate it. So SAT is the set, is a problem. It's one of the elements of NP, which in itself is a set of all Boolean formulas which are satisfiable, and none of the Boolean formulas which are not satisfiable. So when I ask you, is a Boolean formula that I give you, hand you over, is that satisfiable? I'm asking you, is it an element of this set? SAT. I'm just giving you a name. No, everything you want, yeah.
Can you please go again to NP once more? Like what define NP?
Oh, NP. So P is all problems which are solvable in deterministic polynomial type. NP are all problems which are solvable in non-deterministic polynomial type.
What is non-deterministic mean? It can be solved in super polynomial?
No, it could be solved in parallel in polynomial type. So if I give you an unbounded number of processes or threads, and you can run them all together to your heart's content, the total running time will not be more than polynomial in the size of the problem. Instance.
Condition, what if it's exponential, no matter how many resources you have, it's still NP?
If there's no way to solve the problem in general, in worst case polynomial time, if there's no algorithm that exists that can pull this stunt, then it's not in NP. But that doesn't mean it's necessarily exponential because there's things in between. To be fair, there's lots of stuff in between exponential and NP. But it's definitely not in NP if it can't be done in parallel in polynomial time, because that's the definition of NP. It must be able to be done somehow, by some algorithm, or some way, in polynomial time, one way or another. And maybe it's a very complicated algorithm that we're not aware of. But if such an algorithm exists, that problem is still an NP. Question?
And when we say parallel, do we have to deterministically know how many parallel branches, or is that the non-deterministic?
It's unbounded. So there's more and more threads all the time that you can utilize or deploy. You're not restricted. So it seems like, if I say unbounded parallelism, that's a huge gift, computational gift to you. Because most actual machines only have bounded parallelism. An Intel i7 or i9 might have 8 processors or 12 processors. Or if you have an NVIDIA GPU, it might have 1,024 processors or even 1,000,000 processors on high-end stuff, hardware platforms. But 1,000,000 is still bounded. It's not 1,000,000,000 and it's not 1,000,000. Any other questions so far? As we get deeper into it, we'll kind of show more examples and more illustrations, and hopefully it'll gel. I know it's very hard to wrap your mind around everything right now at this point because it's pretty abstract, but you'll get more and more concrete as we go. Yeah.
So, where in practical applications we see that we need to solve SAT kind of problem?
Yeah.
Where do we see it?
Oh, so in many practical applications, you need to solve SAT. When you design hardware circuits. It turns out a lot of problems can be reduced to SAT. A SAT solver can solve thousands of different classes of practical problems that you do every day. Scheduling they can be reduced to SAT. Bin packing, traveling salesman problem can be reduced to SAT. Graph colorability can be reduced to SAT. Graph isomorphism, all sorts of friend or foe systems. All these classes of problems can be reduced to SAT. In fact, all of NP can be reduced to SAT, and that's what makes it NP-complete. So thousands and thousands of practical applications. In fact, there's SAT solver conferences and contests every year. Such a big problems, entire conferences on SAT and SAT only. People bring in their favorite SAT solvers and try to make them more efficient, and they run contests against each other. Which one can solve instances of SAT faster than everybody else, and faster on average, and faster on instant. In general, and faster, on particular hard instances and on practical instances, and they compete against each other, and and all these solutions they use in many other fields. It's such a ubiquitous problem. I know it sounds like an esoteric problem. But that's the beauty of NP-completeness. You take a problem that shows NP-complete, that means it's the hardest in the class. Every other problem in the class reduces to it. If you can solve it efficiently, you can exploit that algorithm to solve it efficiently, into solving everything else efficiently, that reduces into it. And in the case of NP-completeness, it's the entire class of NP that can be solved efficiently. If it can be solved efficiently, then it is NP-complete. Question?
No NP-hard set of
Yeah, so let's complete the picture. So the class out here is co-NP, the complements of NP-complete problems. So if I say, is the Boolean formula satisfiable, the complement of that problem is this Boolean formula not satisfiable? It's just the inverse question. And it's not necessarily equivalent, not in the NP sense. You could easily invert a polynomial time algorithm. If I say, is this list sorted? And you have an algorithm that easily and quickly detects a sorted list, you can easily convert that algorithm to the opposite question, or is this list unsorted? How would you do that? You have a subroutine that can tell you whether a list is sorted. How can you convert it to a subroutine that tells you whether a list is not sorted?
Negate the answer.
Just negate the answer. That's it. But here's the subtle part. If you have a non-deterministic algorithm that tells you, whether a Boolean formula is satisfiable, you can't easily negate that into an algorithm that tells you whether a Boolean formula is not satisfiable. Because the definition of non-determinism, you keep forking processes in the combinations of tree, and you can fork at every variable, yes or no, go left or right, and after n steps, you'll be assigning all the variables to values, and the tree will be exponentially wide, even though only linearly high. As long as one of the processors detect an answer that satisfies the formula, the whole combination can stop and declare victory, and the whole tree spits out the answer, and that's your answer, and you've solved it in non-deterministic polynomial time, because you don't care about the processors that didn't find the answer. It's like sending, giving you all a hard problem to solve, all the same problem, you all, 100 of you, and the first one that finds the solution raises a hand and spits it out, and then everybody settles down, and here's the answer, agrees, and everybody else is done, even though they didn't discover the answer on their own. That's how non-determinism, that's how parallelism works. As long as one of the threads gets you to victory, you win. Doesn't matter what the others do. So keep that in mind. So negating that is not straightforward. Why? Because negating that means all paths must lead to victory, or all paths must lead to defeat. And how do you determine that? You can't do that by running in parallel and waiting for somebody to find something, because you have to wait on all of them now. And some of them can run for an awful long time. And it's not easy to negate a non-deterministic computation using the same complexity, unless you want to, compute the whole tree layer by layer by layer by layer, deterministically, and you can do that. You can backtrack and find another, assign other variables and try that, and back and forth deterministically. But now you have to go through an exponential number of cases, and you're no longer in polynomial time, much less non-deterministic polynomial time, or deterministic polynomial time. So these problems, NP-complete problems, NP-hard problems, it's not that they're hard to solve no matter what. No, they're easy to solve if you have brute force on your side. Cryptography. It protects data by encrypting it. But it's very easy to solve, to break a crypto system if you didn't care about time. How would you do it? Trivially, if time wasn't an issue. Try all puzzle passwords or encryptions, whatever. So it's very easy to guess somebody's password to their bank account if time wasn't an issue. Try all possible strings of 50 characters or less, but there's a Google of them or whatever. And so good luck you putting even a dent in that set. And also, by the way, the system will probably lock you out after 5 false tries, so that's an extra hurdle. But even without that, it's easy to guess passwords if time wasn't an issue. But if you want to do it within the lifespan of our universe, it's really hard. And that's why passwords work. But guessing a password is not inherently impossible. It's just hard to do efficiently. So NP-completeness, another feature or value of NP-completeness, it gives you practical protection against hackers, against intrusions, because you set a situation up where to guess all possibilities will take us so long that nobody can practically do it within a human lifetime or even the lifetime of the universe. And that's when the safety and the protection kicks in. But if time wasn't an issue, it'd be trivial to break the system or guess the password or break into your account. If you had a Google years to do it, yeah, you just try every possibility. So same for SAT, same for any NP-complete problem. They're not impossible to solve. In fact, they're all solvable with a very trivial item, try all possibilities. But in polynomial time, that would be a trick how to do that. And for NP-complete problems, nobody knows how to solve any of them in polynomial time. And if you can solve even one of them in polynomial time, they all immediately become solvable in polynomial time through these transformations. So there are the core NP-complete problems like tautology. Tautology means it's always true. This Boolean formula. And of course, there's problems that are P-complete, like linear programming, LP, linear programming, and P-complete, they're all transformable to one another, but not polynomial time anymore, because it's within polynomial time all to begin with, so you've got to transform using logarithmic space reductions. Just so you know. We won't talk too much about logarithmic space reductions, but the reduction itself can have any kind of time bound, not just polynomial. If it's polynomial time bound and the reduction, and problems come from P, you got P and NP and co-NP. But if it's long space reductions, and you have a whole theory of P-completeness. In fact, every complexity class has its own theory of completeness associated with it. There are problems going to be done in polynomial space, it's called P-space, polynomial space. And there are problems that are P-space complete. There are problems that can be done in exponential time, so there's exponential time completeness and exponential time complete problems. So this theory is not just about P and NP. We know and love P and NP, and it's near and dear to our hearts, so we talk a lot about P and NP. But all these other classes have their own P-NP type questions. Okay. Is non-deterministic exponential time the same as deterministic exponential time? That too is open. Okay. Any questions so far? Again, bear with me. We're getting more and more specific and more concrete. So we don't know if P is equal to NP, but we know that P is equal to co-P. Why? Because you can negate your answer. So I say it's a number of prime, and you can be able to detect primes. You can easily come up with a subroutine that detects non-primes, that detects composites. Now, run the first subroutine that detects a prime, feed it the number you're wondering about. Whatever its answer is, negate the answer. So within P, you can easily negate an answer and come up with an efficient algorithm for the complement of the problem. Identifying composites, not primes. But for NP, you can't do that because you cannot. It's not obvious at all how to negate a non-deterministic computation tree, where the definition of success is there exists some path to victory. Not all paths must lead to victory. One path leads to victory. That's enough for non-deterministic computation. It's like the venture capital model of capitalism. You can fail many times. As long as you succeed once, you'll make a lot of money. So venture capitalists do exactly that. They fund not one company and wait to see what happens. They fund 20 or 30 or 50 companies. And 48 or 49 of them will fail miserably, very quickly in fact. One of them will become Facebook or Google, that pays for all the other 50, 49 and then some. So that's what non-determinism is. One of the paths leads to victory, the whole thing is good. Doesn't matter that there were many other paths to failure. And life is like that in general, if you think about it. Okay. So let's talk more about SAT. So usually the formula is given in conjunctive normal form, so it's a product of sums. For example, here's a Boolean formula. All the x's are Boolean variables, yeses and nos. So instead of calling the x, y, z, I'm just calling the x1, x, because there's going to be many more than the alphabet size. And apostrophe means negation, like x not. Plus means what? Or, and multiplication, parentheses, means and. That's simple. Disjunction and conjunction. What's your function? Okay. So the formula is satisfiable if it can be made true through some assignment of the variables without saying which. But if there exists an assignment of variables, the formula is satisfiable. So now we're kind of giving the formal definition of what we talked about all along. Now we're just writing them down more precisely. So the problem of satisfiability is given an n-variable Boolean formula like this one, is it satisfiable? Is there an assignment of variables that when you plug that assignment into the variable, boils it down to true? And we're not saying that every assignment should do that, but we're saying that it shouldn't be the case that no assignments do that. In other words, there exists at least one, doesn't matter how many more than one, but at least one that does this job, makes it true. So for example, this formula is true. How do we know? Well, you assign x to 1 and z to 0, and you'd have 1 plus something that's true, and z is 0, so this whole clause is true. So true times true is true, so the whole thing is satisfiable through this particular assignment. And it could be other assignments that make it satisfiable, and that's okay too. But this formula is not satisfiable. Why isn't, prove to me that this formula is not satisfiable? Other than, well, okay, let me ask you this. How would you brute force prove that it's not satisfiable if you didn't care about the size of the proof or how long it takes to prove? The answer is very simple. Try all possibilities. Plug in all possible combinations of x, y, and z. And in this simple case, how many are there? The sphere with x and z. Actually, there's only two variables, x and z, so it's really only 4 possibilities. Not too onerous. But in general, there could be a lot of variables. And if you try all possibilities for every single variable, you can have 2 to the n different testings, and that's an exponential time, kind of a test altogether. But here it's relatively simple, right? X plus z must be true if this is satisfiable. So that means not both of them could be 0. One of them must be 1. But if one of the x or the z must be 1, then one of the x prime or z prime must be 0, and they're all conjuncted together, ended together, so that makes the whole thing false. I mean, you can see that argument. Okay, so obviously it's not satisfiable without even having tested all possibilities. So sometimes there's shortcuts, but other times there are no shortcuts that we know of. Okay, so the Cook-Levin theorem is interesting. It was invented by both Stephen Cook and Leonid Levin almost simultaneously in the early 70s. So the theorem is this. Satisfiability is NP-complete. This seemingly harmless, innocuous, innocent-looking problem. If I give you the formula, you tell me if it's satisfiable or not. It seems like, what's so hard about that? Well, what's so hard about that? This is the hardest problem in NP. It's NP-complete. Everything else in NP reduces to it in polynomial time. And we're going to show you a sketch of the proof, not necessarily the whole proof. The whole proof is lots of details. But, anyway, so the idea of the proof is this. Given a non-deterministic polynomial time computation, and we say Turing machine, but it's any computation, and some input, instance of the problem, you can construct a conjunctive normal form Boolean formula that basically mimics the computation of the Turing machine. And there's a lot of details here, but let's just say that this formula will have different clauses that simulates the Turing machine and captures its state at any given time, and where the read-write head of the Turing machine is at any given time, and what the contents of every single cell is at any given time, which character is contained in each cell of the tape of the Turing. Let me not be presumptuous. How do you know what a Turing machine is, how it works? Okay, a lot of you, it's good. If not, you should probably look it up. It's a very simple model of computation where you have a set of states and a transition function in a tape, and you can just go back and forth on the tape and change states and change what the read-write head of the machine points to on the tape. So, without belaboring all these minutiae of this proof, which proof that satisfiability is incomplete, because you can capture, the execution of an arbitrary Turing machine that is non-deterministic. So if the formula comes out to true after the construction is complete, then this is a big reduction. Just like we saw in the slide a few slides ago, A reduces to B with this function f, and this is one of these reductions, reducing a arbitrary non-deterministic Turing machine computation into a Boolean formula such that that Boolean formula is satisfiable if and only if that machine halted on its input if you ran. Okay, that's what the transformation does. So if you can solve satisfiability, you can predict what arbitrary non-deterministic computations will do. And that makes that problem the hardest problem in NP, because all NP reduces to it is we just assume that it's an arbitrary machine that's non-deterministic, runs in polynomial time, and solves an arbitrary problem. We didn't make any assumptions about what that machine does or what problem it solves. We just showed that it can be converted to a Boolean formula. And I've skipped a lot of detail. I don't think it's worth getting into all the minutiae of this transformation. But for extra credit, read it, look it up in the book, look it up on the wiki or whatever, and tell me exactly what's going on. But the thing that you just need to know, never mind the proof, is that SAT is NP-complete. It's everything in NP reduces to SAT, and that's the idea of the proof. And there's even more details than that. This 2 slides are just a sketch of the proof, really. And we won't waste precious time by diving too much deeper into it. But it's an interesting historical note about this. They discovered it around the same time, 1971. Stephen Cook was in the United States, a professor at Berkeley. Leonid Levin was a researcher in the Soviet Union before it broke up. The Iron Curtain was in full swing, the Berlin Wall. They weren't allowed to travel. They had their own conferences internally. Westerners weren't allowed to attend. It was all in Russian. And so nobody knew that this guy solved this amazingly important problem until like a decade later when they figured it out. He actually published it. Leonid Levin did. So did Stephen Cook. But Stephen Cook published it in an English journal, in a mainstream U.S. conference, and everybody looked at it and were amazed, and he got the Turing Award a few years later. Leonid Levin didn't get any credit for it for at least a decade, and eventually they looked back at the Russian publication, and it was only like 1.5 pages, barely more than a page, very, very dense, written in Russian and very cryptic notation in Russian, not just Russian. And so he unfortunately didn't get so much credit for it until much later. But it was a co-discovery that what was that satisfiability is NP-complete. It's the hardest problem in NP. So actually, ironically, Stephen Cook was denied tenure at Berkeley. This is probably Berkeley's worst tenure decision ever, because he got the Turing Award just a few years later, and he invented this entire theory of NP-completeness, won the Turing Award, and became a huge hero. Leonid Levin basically was very obscured by where he lived in the Cold War and how he wrote the result. But he was a student of Andrei Kolmogorov, who invented, pioneered statistical theory and randomness theory and chaos theory back in the Soviet Union in the old days, in the 40s and 50s. So at least he had a very illustrious PhD advisors. So SAT is an NP. How do we know you can solve satisfiability easily using a non-deterministic polynomial time algorithm? Well, take out the first variable, decide whether it's yes or no, and branch into 2 different threads. One thread will assume it's yes, one thread will assume it's no, and keep going. Then each thread will look at the second variable, given the choice of the first variable, and decide whether it's going to be yes or no, and then bifurcate again. And so after n bifurcations, each leaf of this computation tree will have every possible combinations of zeros and ones for the x's, no matter what, how many get this strategy. And then what do you have to do? Test or check whether all the guesses that you made all along actually work. And a lot of these guesses will end up in failure. But if there is a guess that makes this formula satisfiable, namely true, one of these threads will stumble upon it. How many see that? Because between them, they're guessing all possibilities. So that's why it's an NP. Because we just described a non-deterministic algorithm that solves it in polynomial time, non-deterministic polynomial time. Because this algorithm that we just described is actually linear time. How many see that? Because we're just being charged for the height of the tree, not its width. The height is linear. The width is exponential, but it doesn't matter. There are an exponential number of processors at the bottom, all working away, but each one only worked for a polynomial amount of time, in fact, linear amount of time, just making choices between every variable being true or false. So it's called the guess and verify approach, and it works in general for NP-complete problems using non-determinism. The trick is to do all this deterministically with a single thread, not unbounded number of threads of parallelism. And by the way, earlier we asked why is determinism a special case of non-determinism? Because if you have the choice of bifurcating at every stage, that's a direct generalization of not bifurcating, just taking one choice, being a deterministic choice. The other way of saying it you have the option, but not the obligation, to bifurcate. So if you have a massive parallel machine, you can still run it in serial. You can still just use one processor only and not deploy the others. You have that choice. Now your machine is not parallel, it's serial machine, even though it has potential parallelism, you're not using it. How do you get this? You don't have to use it. You could use it if you want. If you're using parallelism, it's NP-complete. It's a non-deterministic computation. If you're not using parallelism, it's a deterministic computation. But one completely subsumes the other because it's the right to use parallelism, not the obligation to do so. Okay. And that's why P is a subset of NP. All right. So you can think about NP as being characterized by the verified property. It's a set of all problems for which proposed solutions can be quickly verified. That's equivalent, if you think about it. And it's also a set of languages or problems for which membership can be quickly tested. By quickly, we mean polynomial time. So whenever you see quickly or efficiently or effectively or in a tractable way, the clock is running and it's polynomial time. Okay. It's not, in particular, it's not exponential time or anything else like that. It's polynomial time. So here's Cook's paper, actually. This is the original paper. One author, 1971, and he actually comes on the right and says it right in the first sentence of the abstract. He says, it is shown that any recognition problem solved by a polynomial time-bounded non-deterministic machine can be reduced to the problem of determining whether a given Boolean formula is a tautology, satisfiable or not. So he actually not only proves it, he knows the significance of his own proof. When this first came out, it wasn't obvious to all the people reading this paper how monumental this paper is. One guy that recognized it right away was Richard Karp, and he wrote a follow-up paper, and we'll talk about that paper a little bit later, next time, I guess. But here is the Leonid Levine paper. This is not just the first page of this paper, it's his entire paper. And even if you understand Russian, how many here speak Russian? Okay. No collusion, just Russian. So even if you understand Russian, it's very, very hard to read this thing. It's very dense and full of esoteric notation. And because in the Soviet Union back in those days, when you published papers, they would charge you by the page. And so authors had a huge incentive to compress everything into fewest words and fewest pages as possible, because they couldn't afford, they were getting paid just a few bucks a month or something, a ridiculously low sub-wage, sub-wage kind of salaries. And publishing a paper can set them back like 2 weeks of pay or something. That's not feasible. So very, very dense paper. By the way, if you look carefully at episodes of The Simpsons, you see very interesting mathematical relationships and theorems. Here's P is equal to NP in here, and here's Euler's formula right there. E to the pi I is equal to -1. Some people call this the most beautiful formula in all mathematics. It involves all the famous constants, E, pi, 1, and I, and has subtraction, multiplication, exponentiation, and so it's just an amazing formula. Anyway, the Simpsons show has mathematicians on staff whose job is to insert these mathematical Easter eggs into the episodes. If you're so inclined, you can keep that like that. Okay, so fast forward a few years later, Gary and Johnson published a kind of encyclopedia of NP-complete problems. When Cook came up with his paper, all we knew was NP-complete was satisfiability. We thought, okay, that's a hard problem, even though it seems innocent. Fine. Maybe it's a quirk, maybe some esoteric problem, that has this property that all NP reduces to it. It turns out that it's not an exception, it's the rule. It's a wide phenomenon. Almost every interesting problem you can think of and have trouble solving is NP-complete. Scheduling classes every semester among N students and M classes, that's an NP-complete problem, actually. It's the problem of scheduling. So now you know why it's so hard for you to form a schedule at the beginning of every semester. It's not just tricky, it's actually NP-complete. We have no known polynomial time deterministic algorithms to schedule. We have a lot of heuristics, and so do you. Otherwise, you wouldn't be here, you'd still be moving for classes months later. But in general, it's a very hard problem, scheduling. And Gary and Johnson listed an encyclopedic collection of hundreds and hundreds of problems, which are all not just NP-complete, they're all practical problems that people have been trying to solve for decades efficiently, and they all failed and didn't know why. But now we know why. They're all NP-complete. So if you can solve one efficiently, all of NP can be solved efficiently too, because everybody worked on lots of problems NP separately, thinking they're individual, independent problems that have nothing to do with each other. They worked on them separately. All of them failed to solve them, not knowing they're all tied together by this theory of NP-completeness. But if any one of them succeeded in solving any one of those problems that are NP-complete, the entire class will fall instantly and all be solvable with polynomial time deterministically right away. And that explains why it's so hard to solve any one of them. Because by solving one of them, you solve them all, and they're all different. And people have worked on all of them separately for many years, not even knowing they're related by this transformation. So, very powerful phenomena. And it gives lots and lots of reductions and transformations. And this cartoon is right out of the book. And by the way, the book is on the website, so feel free to look it up. You don't have to read from the cover, obviously. It's an encyclopedia of NP-complete problems. But it has also explanations of NP-completeness at the beginning of the book. And so does the Corman book, the course textbook. You should look there. But it shows you this cartoon. This cartoon, this guy comes to his boss at a company they worked at, and he said, instead of saying to your boss, I worked on this problem for many months, I couldn't solve it, sorry. Maybe I'm not smart enough to work at this company then, who knows. Now that guy can say something much more interesting to his boss when he failed to solve the problem. He said, yeah, I couldn't solve the problem efficiently, but I did prove it's NP-complete. Because it's NP-complete, not only I couldn't solve it efficiently, nobody can solve it efficiently. Because if they could, P wouldn't be equal to NP, it wouldn't be open anymore. That's a much more clever, powerful, impressive thing to say to your boss than I tried and failed, sorry, I don't know why. Which is what happened up to that time, many places around the world, in labs and companies and governments and academia. People would fail to solve, to find efficient solutions, and really didn't know why, other than the obvious reasons. Maybe they weren't smart enough, maybe they didn't work on it hard enough, maybe they didn't have the right insight. But now we know why, because all these problems are bundled together in this very strong set. So not surprising that they couldn't solve that particular problem that they worked on. Because if they did, they would solve all the other problems simultaneously, instantly. And that's a lot to ask for. So if they fail in doing that, it's no shame. But it's actually the expected case. So anyway, that's a pretty good book. And NP and P are robust. They're independent of the model of computation. There's many models of computation. Right? Turing machine is one. Abacus is another. They're all equivalent. Boolean circuits is another. You can compute using polynomials. You can compute using mu system. Even billiards. It turns out that the game of billiards is as general as arbitrary computations. If you set the balls just right in a billiards game, and we're talking about a generalized billiards, I mean, field, the table could be arbitrarily large with the arbitrary number of balls. You can compute using these collisions of billiards balls, it turns out. You can construct AND gates and OR gates using collisions, and where balls go, you can reach pockets. And the billiard table could act as a generalized, arbitrarily arbitrary computation. How many knew that or ran into that? How many heard of the game of life? Conway's game of life? Good, a bunch of you. That's a generalized computation model too. So deciding whether a game of life configuration ever halts, it's undecided. It's a general computation. In general, it's scenarios in life that do arbitrary computation. So is orbital mechanics, so is DNA computing, and there's lots of ways to compute, and they're all equivalent. And the definition of P and NP apply to all of them in the exact same way. The class P and NP are the same for a supercomputer, for a Turing machine, or for an abacus, or for Boolean circuits, or for a game of life, or any other. It's exactly the same class. So it's robust. It's independent of the underlying device that we use to compute with. That's another advantage of these classes and this study of NP-completeness. It studies arbitrary computation models all at once, all in the same way. Not just a Dell, and then later an Apple, and then later an iPhone, and later some computer that hasn't been invented yet. NP and P apply to all of them. So and by the way, I keep saying it's $1 million prize, and here's the actual website that offers $1 million for each one of those problems. There's 7 of them. And one of these problems was already solved, the Poincare conjecture. Perlman solved it in 2006, won the Fields Medal for doing that. And didn't want to collect, and he won the Millennium Prize problem, $1 million, $7 million for the 7 problems. Literally, they're worth $1 million bounty each, and he refused to collect $1 million. When asked why, he says that he lives in I think he lives in St. Petersburg, and he said that it's dangerous for someone to live in St. Petersburg and become famous for getting $1 million cash bounty for solving some problem. It's becomes a personal safety hazard. But of course, he had other reasons for that. He's an interesting character. And P is equal to NP, that problem is still on there, so it's still not solved. And many of these problems were originally named by David Hilbert in his famous speech to the Mathematics Congress in Paris in the year 1900. If you study him for a while, he himself is a fascinating character and made a huge impact on mathematics and indirectly on computer science. So, any questions or comments? And I know some of this was abstract, but I urge you to read the section of the book that discusses this and other books that I made available to you that discuss it, or the weekly pages, lots of ways to kind of nail down your knowledge and comfort level with these concepts. Because we're going to go deeper into NP-completeness for the next 2 or 3 lectures. It's going to be fun. All right. Anything else? Yeah.
Because you say every problem in NP has to boil down to that.
Has to be reducible to that NP hard problem. Yeah.
All problems are in NP, make sure that all of them.
Just like Stephen Cookie, he's saying, how do you know that you reduce all of them? Well, by reducing a generic computation, NP computation, non-deterministic one-time computation, to that problem, you've reduced them all essentially, because you reduce an arbitrary Turing machine that works in non-deterministic one time without making any assumptions about how it works. So essentially, it can simulate any non-deterministic computation. But once you know one problem is NP-complete, all you got to do is reduce that to the unknown problem, and then compose the 2 reductions. So it's a very, very good question you're asking. So you don't have to do it generically every time. Once you reduce all of NP to a problem, and you want to reduce all of NP to another problem, just reduce this problem, this one single problem, to the other one, and the composition of the 2 reductions does the job. And we'll talk a lot more about that next time and the time after that. All right. If there's no more questions, we'll see you next time. But do read about that stuff. It's subtle, but it's fun and it's fascinating.
Like